we've set the flag that indicates that this is a FLIX lecture, which stands for Fantastic Lectures in Computer Science. And we're very fortunate to have a fascinating speaker with us today. But before we get started, a couple reminders. The graduate students who are here, who are funded students, make sure you sign in on the sign-in sheet. And after the talk, we will reconvene in the Computer Science Department library, which is Mendel 159. If you'd like to continue the conversation in a more informal setting, we welcome and encourage you to come down for that. We have some light refreshments and no wine. Unfortunately, this is not the biology department, so we haven't figured out the deal yet. But nevertheless. Oh, and before we talk, just to get everyone warmed up, make sure you're ready for algorithmic thinking and thinking through puzzles and that sort of thing. I need you to do one limbering up exercise, and that's using your hands. I'd like you to hold your hands out in front of you, like that. You do, Phil. All right, everyone hold your hands out like this. All right, point your thumbs toward each other. Now take your thumbs and point them down, cross your arms, and lace your fingers together like that. Now make sure your thumbs are still pointing down. Okay, good. Now very slowly take your thumbs and turn them to one side or the other, just a little bit. And you notice it hurts a little bit, right? So turn a little bit more, and then just keep turning and turning and turning until it goes all the way up like that.
I'm good.
So now you should get ready for today's speaker. Professor Anany Levitin is a member of the Department of Computing Sciences, and he specializes in teaching algorithms. In fact, he wrote the book on algorithms, quite literally, one of the most widely used textbooks on algorithms. And we're very fortunate to have him here today. To anyone in the room who has studied algorithms, which hopefully is everyone, in one form or another, it really is the foundation of computing science, and the foundation of so much more, including a skill that would help you well in your job search. So it's a fascinating topic and a fascinating speaker. Please welcome Professor Anany Levitin.
Well, thank you for this nice introduction. Let me disappoint you. First of all, I cannot match this. Second of all, I cannot tell whether it was an algorithmic puzzle or it was not. So it's a clear sequence of directions, but I failed to follow them. So they were not clearly defined. Well, thanks again for providing me with an opportunity giving this talk. And thank you all for coming instead of enjoying this wonderful weather outside. I do appreciate it. I'm going to talk about algorithmic puzzles. Here is the plan of my talk. First, I'll explain what I mean by an algorithmic puzzle and give two taxonomies of them. I'll talk briefly about algorithmic puzzles in research, then talk about problem solving in general, algorithmic problem solving in particular, and discuss how puzzles fit into the picture. And if the time permits, because there are many students here, I'll end up with discussing using puzzles during job interviews. So informally, an algorithm is a sequence of unambiguous instructions for solving a problem, and most dictionaries define a puzzle as a problem that challenges ingenuity. So an algorithmic puzzle is a puzzle that involves the design or analysis of an algorithm. Actually, algorithmic puzzles are quite old. In a 12-years-old collection attributed to Alcuin of York, one can find 3 river crossing puzzles. So the collection is dated 800 CE, and you can appreciate the point. So Al-Khwarizmi, after whom the notion of algorithms is named, was already alive, but was about only 20 years old. So surprisingly, it took quite long for humankind to recognize algorithmic puzzles as a special category of puzzles. It's only in 1987, A.K. Dewdney, who wrote a column following Martin Gardner for a while in Scientific American, published an article when he used the term alga puzzles. 5 years later, Dennis Shasha, who is a professor of computer science in NYU, published a book titled Dr. Ecker's Cyber Puzzles, which contained about 2,000 puzzles embedded in short stories. And 2 years later, Peter Winkler, who used to be a head of research in Bell Labs and now teaches at Dartmouth, published a wonderful collection of difficult mathematical puzzles. And in that collection, he had a chapter containing 7 algorithmic puzzles. So in last year, I and my wife published a book. Well, we didn't publish it. Oxford published it. We wrote it. It's a large collection of algorithmic puzzles. It starts with a 30-page tutorial with 22 puzzles as examples. And it's followed with 150 other algorithmic puzzles divided into 3 difficulty levels. I would love to discuss all 172 puzzles with you, but I'm afraid I will run out of time. So algorithmic puzzles can be classified in 2 different ways. They can be classified either by puzzle types or by algorithmic questions posed. Here are some types of algorithmic puzzles: river crossing and similar problems, weighing, measuring, and cutting puzzles, moving counter problems, state-changing puzzles, including puzzles involving coin turning and pancake frying, chessboard problems, which include the most well-known of those, 8 queens problem and knight's tours, route and tracing puzzles, tiling problems, magic squares and related problems, sliding piece puzzles, and one-person games such as Chinese rings in better-known Tower of Hanoi. Alternatively, as I mentioned, algorithmic puzzles can be classified by types of algorithmic questions posed. We can be asked to find for a given input the output of a given algorithm. We can be asked to find an input yielding a required output by a given algorithm, or to find the number of steps needed to solve a puzzle by a given algorithm, or to design an algorithm for solving a given puzzle, often in a minimum number of moves. It's in red because it's by far the most important category of puzzles. And finally, there are puzzles we have to show that the puzzle has no solution with operations allowed by the puzzle. Here is an example of a puzzle when we have to find an algorithm's output. It's a famous Fibonacci's rabbit problem that many of you know from a course in discrete structures. A man put a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that pair in a year if it is supposed that every month each pair begets a new pair, which from the second month on becomes productive? Here's a nice diagram, what's going on. And on the right, we have the number of pairs after each month. And those numbers form that remarkable sequence known nowadays as the Fibonacci numbers. In this version, it starts with 2 ones, and each new term is obtained as the sum of its 2 immediate predecessors. I have 2 examples of problems when we ask to find an algorithm's input which is produced by a given algorithm. The first is an old and well-known Josephus problem, which is based on an episode in a Jewish revolt against the Romans 2,000 years ago. There are n people numbered 1 to n standing in a circle. Starting the count with person number 1, every second person is eliminated until only 1 person is left. And the question is, where in a circle should a person stand to remain the last person standing? And here, a much newer problem. A virus spreads through squares of an n by n chessboard, infecting squares that have 2 infected neighbors, horizontally, vertically, but not diagonally. What is the smallest subset of unit squares that need to be infected initially for the virus to spread to the entire board? Actually, it's not difficult at all to give several subsets of n squares whose initial infection will eventually infect the entire board. Which is difficult to prove is that n is a minimal number of squares which can do the job. It's a very interesting puzzle. Surprisingly, there are few puzzles when we are asked to find an algorithm's number of steps. But here is one such puzzle, a single elimination. We have a single elimination tournament, which can be considered an algorithm, actually. And the question is, how many matches in total does it take to determine a winner among n players, and how many rounds need to be played? Both questions are very easy. Actually, more interesting question is about the number of buys. A buy is a promotion of a player to the next round if the player does not have any opponent to play. And an interesting question is to count the number of buys. Actually, there are two different ways and two different by related formulas to compute the number of buys. Finally, we came to the most important class of algorithmic puzzles when we ask to design an algorithm for a given puzzle. So I have two comments about it. First of all, it goes without saying that most algorithmic puzzles can be theoretically solved by exhaustive search. That is, by generating and checking all potential solutions, or by its more intelligent version called backtracking, but a more efficient solution is usually expected. And the second point, that algorithm design puzzles can be further classified by the solutions design strategies, which I am listing on the next slide. There are 9 of them. Brute force with exhaustive search is a special case. Backtracking and branch and bound. Decrease and conquer, divide and conquer, transform and conquer, greedy approach, iterative improvement in dynamic programming. Well, I would love to explain what those strategies are and illustrate them with puzzles, but it will take a lot of time. I'll just give an example of one strategy and an example illustrating it. It's a divide and conquer. It works as follows. We divide a given problem into 2 or more smaller subproblems, solve the smaller subproblems somehow, usually recursively, and then combine the solution to the subproblems to get a solution to the problem given. Here is an example. My students probably get tired of it because I give it in 1300 course on discrete structures, in algorithms course. But it's a perfect, beautiful illustration of divide and conquer. So the puzzle is to cover any 2 to the n by 2 to the n chessboard with one missing square with right dominoes, which are L-shaped tiles of 3 adjacent squares. One such tile is shown in the black on the left. The puzzle was invented by Solomon Golomb, then a math graduate student in Harvard in the early 1950s. Of course, in the early 1950s, there were just few computers around. Nobody has ever heard about divide and conquer. And actually, Golomb was motivated by Bolzano-Weierstrass theorem. How and why, I don't know. Anyway, it's an important theorem from calculus. Here is a beautiful solution. We place one domino at the center of the board to orient it so that to cover 3 central unit squares that are not in the smaller subboard with the missing square given. This immediately reduces the problem to tiling the 4 smaller subboards, each with one missing square, which can be done by the same method, that is recursively. I was so enamored with this puzzle that we put this puzzle on the cover of our book. Well, some people believe that divide and conquer has applications in real life and even outside of the realm of politics, which is a cartoon depicting one such application. Well, it is why you should study algorithm design techniques. You never know when they can be helpful. Finally, puzzles with no solutions. I'll give 3 well-known examples. Maybe the best known is the 7 bridges of Knigsberg, solved by young Leonhard Euler in 1736. We have a scheme of an old city of Knigsberg with a river Pregel with 7 bridges. And the question was to find the walks through the city that would cross each bridge once and only once. Euler proved that it was impossible to do. By the way, it is a very well-known problem. What is not that well-known, that in his paper, Euler explicitly wrote that he used the idea of Leibniz, that Leibniz somewhere wrote that it would be interesting to develop the geometry of position as opposed to geometry of distances. So if you think about it, Euclidean geometry is actually geometry of distances. We consider, say, 2 segments equal to each other or congruent if we can place one on the other and then coincide. So the distances are fixed. What Leibniz was interested in developing of a geometry, we wouldn't be interested in relative positions of objects, and presumably it motivated Euler to solve this problem. I'll return to this briefly later when I talk about research in puzzles. The second well-known puzzle with no solution is the 15 puzzle, whose precursor was invented by Noyes Chapman, a postmaster in Canastota, New York. The instance below was popularized by Sam Lloyd, America's greatest puzzle creator, till his death claimed that he was the one who invented the puzzle. Well, actually, people now believe that at best he invented this particular instance shown here. In this puzzle, we have a box with 15 tiles numbered 1 through 15, and one should shift the tiles with an object of getting from an initial configuration to the configuration where the slides are in numerical order. And for this particular configuration on the left, there is no solution, and it is why Lloyd offered a $1,000 reward for a person who would be first to solve the puzzle. There was a craze in 1870s when people spent hours and hours trying to get $1,000 by solving the puzzle. And here is another well-known problem without a solution. It's a tiling a mutilated chessboard with dominoes. Martin Gardner mentioned it in his 1957 column in Scientific American. Gardner didn't invent the puzzle. It was probably invented somewhere around 10 years earlier. It's not quite clear by whom. The puzzle is 2 tiles that is covered exactly with no overlaps, an 8x8 board with 2 diagonally opposite corners with dominoes, which are 2x1 rectangles, which can be oriented either horizontally or vertically. And again, the problem does not have a solution, and it can be proved by 1-sentence argument. Now, puzzles in research. 2 puzzles indeed played a historical role in mathematics. The first is the Fibonacci's rabbits problem, because it introduced Europeans to the sequence we now call Fibonacci numbers. Actually, it turns out that in India, Fibonacci numbers were known for more than 1,000 years before Fibonacci, but still it is how Fibonacci numbers were introduced in the European culture and then in modern mathematics. Fibonacci numbers still investigated. There is a journal published quarterly dealing with their properties and their applications. people even speculate on stock market using Fibonacci numbers, so it's a very important topic. In the second, of course, is the 7 bridges of Knigsberg, which is considered a cornerstone on which both topology and graph theory eventually grew up from. The next is a traveling salesman problem. It's a problem to find the shortest tours through n cities that visits every city once before returning to the tour's starting city. This problem has been tormenting computer scientists for the last 60 years, and therefore they are disinclined to call it a puzzle, but it clearly has a puzzle flavor. The question about this problem is whether or not it can be solved in polynomial time, which means that is significantly faster than by exhaustive search. In scientific terms, it means, or stated as a P versus NP, or P is not equal NP conjecture. In the Clay Mathematics Institute, established in year 2000, and $1 million prize for an answer to this dilemma. It's definitely the most important open problem in theoretical computer science, and one of the 7, now 6, most important open problems in mathematics after Poincare conjecture was recently solved. There's some research going on dealing with algorithms for specific puzzles. The latest breakthrough concerns Rubik's Cube. 2 years ago, people finally proved that any configuration of a Rubik's Cube can be solved in no more than 20 moves. And there are configurations which do require this number, which makes 20 the so-called God's number for this puzzle. But most of the research in puzzles, or serious research, is done about puzzle complexity, when people routinely prove that one or another puzzle is at least NP complete, which means that it is at least as difficult as a traveling salesman problem. It includes such puzzles as cryptarisms or Sudoku, generalized accordingly to fall under a general umbrella for such investigation. Eric Demain in MIT recently published a book with his PhD student about complexity of many puzzles. Now I want to talk about puzzles in education. So what's so good about puzzles in education? Well, first, they help developing problem-solving skills and creativity. They attract more interest on the part of students, making them work harder on the problems assigned to them. They may seem less intimidating to less prepared students. They force students to think about algorithms on a more abstract level, divorced from programming and computer language minutiae. And finally, they're excellent subjects for project assignments and independent research. It's, of course, a very old idea. I already mentioned Alcuin's collection, dated 800 CE, which contains 3 river crossing puzzles, including the famous wolf, goat, cabbage puzzle, and slightly less well-known 3 jealous husbands. But what I want to stress here is the title of this collection. It was called Problems to Sharpen the Young, which clearly implies an educational purpose of that collection. Here is a modern quote: "There is no better way to relieve the tedium than by injecting recreational topics into a course, topics strongly tinged with elements of play, humor, beauty, and surprise." This quote belongs to Martin Gardner, an American writer, best known for his mathematical games column in Scientific American, which he ran for 25 years. and his columns were so influential that he was voted as one of the 10 most influential mathematicians of the 20th century. Also, he had no formal math training beyond the high school. A new push for using puzzles in education actually came recently from Australia. It was spearheaded by Zbigniew Michalowicz, which is a Polish mathematician nowadays teaching there. So let me give the floor to Australians to speak for themselves.
It's been said that the key element for any problem-solving activity is to understand the problem. It is this thought that is the driving force behind the development of an exciting new learning program, puzzle-based learning. Professor Zbigniew Michalowicz from the School of Computer Science at the University of Adelaide is the writer and developer of this unique course.
And I was involved in educational institutions all my life, working with younger and older students and so on, and always I had a feeling that something is missing in the program. And over the last 10 years I've been experimenting with on different levels in different countries, on different continents, with a variety of puzzles, introducing them gradually in a variety of courses, and always responses were fantastic. You know what? I need a little bit more information. And the father replied, sure, here it goes. My oldest son has blue eyes. And mathematician said, that's sufficient. And he gave immediately the answer. And the question is, you have to replicate the process. You have to discover what was the age of the first son, second son, and third son.
It's unique because it's unstructured. So you don't have a formal curriculum in the sense that you look for another subject.
I think the puzzle-based learning is a great way to excite the students' interest. I think it gives them a great in to learning about fundamental material.
It teaches you how to think, yes, terms out of the box, but think in such a way that you look at problems in a completely different light.
Whether that's about mathematical aspects, computing aspects, general problem-solving techniques.
I think that there's a number of benefits in taking this course because it introduces students to solving actual problems.
As you go through life, you have all sorts of problems, whether you're putting up a shed in the back garden or working out the best mortgage, you need a whole lot of reference points. And puzzle-based learning, I think, will last in everything you do, not just in academic life.
One of the exciting aspects of puzzle-based learning is the interest it receives from those who sit the course and their ability to apply this teaching across the board to other subjects and areas of life.
I'm a big fan of puzzle-based learning, and I mean, I'm really into thinking in different ways and kind of trying to get a different perspective on things, which is really great. Well, it's what the course is doing.
It does help us look at problems differently, and you look out of the forest, as my teacher used to say.
It forces you to think in different ways. It forces you to analyze how you look at problems and how you solve them.
I guess you can look at problems that you initially would think of as having a completely different solution to the real solution, then I guess that'll help in more real-life applications. So I liked it.
I think it's important because it engages them very quickly in the learning process. Having been to one of the lectures that Zbigniew has given, I walked down the stairs in this building afterwards, and I don't think students knew who I was, but there were quite a few of them around me, and I've never heard a group of students so excited and engaged about the lecture before.
Well, how's that for infomercial? So, what's going on puzzles in modern higher education? If few schools do run puzzle-based courses, they include Carnegie Mellon, University of Vermont, UNC Charlotte, University of Colorado, and Colorado Springs, UCSB, Virginia Tech, a few foreign schools, Australia, of course, Israel, Japan, and Poland. And I'm going to teach an honors course at Villanova this fall. Typically, there are two types of the courses. It's either a 3-credit course or 1 credit embedded in an introductory engineering or problem-solving courses. Now, in the next few slides, I'm going to show that main computer science ideas can be nicely illustrated with algorithmic puzzles, starting with the notion of an algorithm. To demonstrate that notion, one can use river crossing puzzles, detecting a light or fake coin with a balance, or the following more sophisticated example. Pay attention. So here is a puzzle. You have a computer game. In this game, a spy is located on a one-dimensional line. At time 0, the spy is at location A. With each time interval, the spy moves B units to the right or to the left, depending on the sign of B. But A and B are fixed integers, but they are known to you. Your goal is to identify the spy's location by asking in each time interval, starting at time 0, whether the spy is currently at some location of your choosing. For example, you can ask whether the spy is currently at location 19, to which you will receive a truthful yes/no answer. If the answer is yes, you reach your goal. If the answer is no, you can ask the next time whether the spy is at the same or another location of your choice. In the puzzle, or the problem is to devise an algorithm that will find the spy after a finite number of questions. Well, it took me more than 2 minutes to solve this puzzle, but for you I cannot give more than 2 minutes, but I will help you with the music. Well, the time is up. Well, the next important idea is that of a recursive algorithm. It's traditional to introduce people to the idea of recursive algorithm by using a Tau of Hanoi. It's a puzzle invented by French mathematician Edouard Lucas in 1883. I know that 99% of you know this, but I'll read this anyway. There are n disks of different sizes and 3 pegs. Initially, all the disks on the first peg in order of size, the largest on the bottom and the smallest on top. The objective is to transfer all the disks to another peg by a sequence of moves. Only one disk can be moved at a time, and it's forbidden to place a larger disk on the top of a smaller one. What is interesting about this puzzle is that if we extend it and consider the same puzzle with more than 3 pegs, there is no optimal algorithm known for the puzzle. There is a conjecture what the algorithm would be optimal, but the optimality of that suggestion has never been proved. I already mentioned 9 general algorithm design strategies, and the fact that it can be nicely illustrated by algorithmic puzzles, showing applicability of the strategies to problems outside traditional computing domain. Again, because of a lack of time, I cannot do it, but in my book on design and analysis of algorithms, there are about 80 puzzles which illustrate basic algorithm design strategies. In the book on algorithmic puzzles, the puzzles are indexed by design strategies and analysis techniques, so it also can be used for that purpose. And actually 10 years ago, I with Mariangela Popalaskari gave a talk at the 60 conference about this topic. So it's a natural question, what changed in 10 years? Now, for one thing, we are older now, but seriously speaking, 2 things changed. In the time, we knew probably a couple of dozen puzzles to illustrate design strategies. Now we know close to 200 such puzzles. And second, 10 years ago, we talked about importance or usefulness of puzzles to teach algorithms to computer science students. Nowadays, there is a general opinion that algorithmic thinking should be taught to students in all majors, and puzzles is particularly convenient for doing that. I'll talk about it later. Finally, again, one of the main ideas in computer science that not all puzzles or not all problems can be solved, and it can be illustrated by puzzles. And solvability of a problem is usually proved in the puzzle domain by finding an invariant, which is a property that does not change by any of the operations allowed in the problem. And most such problems are solved by invariants which fall into two categories: parity and coloring. In particular, 7 bridges of Knigsberg and the 15th puzzle are solved by a parity argument, in many tiling problem and some chessboard tour problems are solved by a coloring invariant. Now, of course, one of the issues in computer science is that of algorithm efficiency, and it can be nicely demonstrated by using the false coin problem, when one is asked to find a lighter fake among n coins with a balanced scale without any weights. Incidentally, it is a puzzle which is very often asked during interviews, say for 8 coins. Well, by brute force, you can simply weigh coins in pairs, one versus another. It's very inefficient because in the worst case it requires n-1 weighings. A much better idea is divide by half. We divide the coins into 2 halves, leaving 1 coin aside if n is odd, and compare their weights. And if they weigh, after 1 weighing, the size of the problem is reduced by half. In wherein lies a trap. So it appears that it's an optimal algorithm, which is not. Actually, at least for larger n, a better idea to divide the coins not into 2 halves, but into 3 about equal subsets, because it reduces the total number of weighings. Because in 1 weighing, roughly speaking, you decrease the size of the problem by a factor of 3, not 2. Now, I want to finish this segment of my talk by giving you a very cute puzzle. It can be called Schweig's puzzle, after the hero of a novel, The Good Soldier Schweig. It's well known in Europe, I'm not sure about America, by the Czech writer Jaroslav Hasek. In this satirical novel, Schweig is depicted as a simple-minded man who appears to be eager to execute orders, but does it in a manner that in fact contradicts the intended goal. So here is a puzzle. The good soldier Schweig had been ordered to line up a band of new recruits. The desired line was required to minimize the average difference in height of adjacent men. Schweig put the tallest recruit first, the shortest one last, and let the remaining men stand between them in random order. Did Schweig execute his order as stated? So here is a 5-man instance of this problem. So I have 2 questions, one to the students in the audience, and the other to the professors. So the question to the students: is the average difference in height of adjacent men indeed minimized in this line? And to the professors, what mathematical fact, which is occasionally useful for algorithm analysis, does the puzzle demonstrate? Again, I'll help you with the music by playing an Austro-Hungarian military march. Here we go. All right. Let's talk about algorithmic thinking. Proliferation of computers in all spheres of our lives made computational thinking a buzzword, at least in computer science circles. So computational thinking is a problem-solving approach named for its extensive use of computer science techniques. The term was first used, in fact, by Seymour Papert of the Log of Fame in 1996. And 10 years later, Janet Wing, who is the head of computer science department at Carnegie Mellon, published a very influential 3-page paper or article claiming that computational thinking is so important that it should be considered on a par with the well-accepted 3 basic skills: reading, writing, and arithmetic. And though she mentioned algorithms in her paper only 3 times, it is clear that algorithmic thinking is arguably the main component of computational thinking. This observing increasing importance of algorithmic methods in sciences from biology to sociology, Bernard Chazelle, in his talk in Bryn Mawr 3 years ago in this Flick series, said that algorithms coming of age as a new language of science promises to be the most disruptive scientific development since quantum mechanics. So it might well be that in the 21st century, algorithms will play the same role for sciences as mathematics played in the last 4 centuries. Let me now talk about problem solving in general, in particular about problem solving strategies. I'm going to quote to you a take on problem solving by in 3 parts. First by a famous physicist, then by a prominent mathematician, and thirdly by computer science. First, here is, let me talk about Richard Feynman, who was arguably one of the most brilliant physicists of the 20th century. A fellow physicist joked that Feynman solved problems by what has become known as the Feynman problem-solving algorithm. Here it goes. Step 1, write down the problem. Step 2, think very hard. Step 3, write down the answer. Well, if you're a genius like Feynman, it probably will suffice, but the rest of us need more specific help. So the most well-known problem about general solving strategies, at least as mathematical problems is concerned, were given by George Paulé, a prominent Hungarian mathematician who moved to the United States since 1940 and taught in Stanford. In 1945, he published a very short book titled How to Solve It, and it was bestseller since then. It's still in print. I don't know how many languages it was translated. I read it in my early 20s in Russian. So in this book, Paulé offered the 4-step plan. Step 1, understand the problem. Step 2, devise a plan. Step 3, carry out the plan. And step 4, look back. To be fair, he went much farther than Feynman. He elaborated or enhanced his plan with 67 heuristics. Well, it's not 67 factorial, but still 67 is a very large number, and it's hard to remember them if you deal with a specific problem. Let's now see what computer science have to offer. It can offer several general problem-solving strategies. There are 9 of them. I already listed them on a different slide. And what's nice about this list, but first of all, it's relatively short, and second of all, most of these strategies are reasonably constructive. In other words, given a problem, it is more or less clear what each of those strategies suggests the solver to do. And I firmly believe that this is what computer science should be selling to the world, both to the world of skeptical academic administrators and to the world at large. Now let me say about algorithmic puzzle-based course for other majors. Algorithmic puzzles can help teaching algorithmic thinking without traditional computer science background and computer programming, putting to rest a wrong idea that computer science is the same as computer programming. And in such a course, the major objective should be appreciation of a concept concept of algorithm, including that of a recursive algorithm, familiarity with major algorithm design strategies, some familiarity with importance of algorithm efficiency, and finally, recognition of problems that have no algorithmic solution. Now, it is more or less a course I'm planning to teach in the fall, and it's somewhat different from that course offered or advocated by Australians. They're using all kinds of puzzles, including logic puzzles and brain teasers of all kinds, and I'm going to concentrate on algorithmic puzzles only. And it's an interesting question, what is a better approach to teach students just general problem solving, even though or it's better to concentrate on algorithmic thinking only? I don't know the answer yet. Let me briefly talk about algorithmic puzzles in K-12 education. The same Janet Wink was quoted in the Pittsburgh Tribune Review by saying that most US students are not exposed to computer science in the same way they are to biology and physics. We have to incorporate computer science at the K-12 level. It is not easy to do, but this is what is needed, she wrote or said. And my point is that algorithmic puzzles are particularly attractive for the pre-college exposure to algorithmic problem solving. To my frequent trip to Russia, I found in a bookstore a book. It was a supplement to the Russian course on informatics for grades 5 and 6. Here is a list of chapters in this book: patterns, sorting, one-to-one correspondence, problems about liars, river crossing problems, decanting problems, weighing problems, combinatorial problems, numeral systems, and game strategies. I'm not saying that every Russian youngster can handle it, but what I'm saying is that at least a noticeable number of them can, otherwise they wouldn't have published the book. And if it is the case, then there is no reason to believe that American youngsters cannot handle it either. Well, here is a summary of the main part of the talk. Algorithmic puzzles is an interesting puzzle genre, still underappreciated, but exceptionally promising for growth in its importance. Problem solving is increasingly understood as algorithmic problem solving. Algorithmic puzzles can illustrate main ideas of computer science, and in particular, they show that algorithm design strategies are general problem-solving tools with applications outside traditional computer science domain. And one last point, though it's very important. In addition to all the utilitarian benefits of algorithmic puzzles, one should keep in mind that the best of them are remarkable and inspiring products of human ingenuity and wit. Well, I still have 3 minutes and 20 seconds. So maybe, should I talk about interviews? Let's talk about them. For the sake of students present, let's talk about puzzles and technical interviews. Until recently, puzzles were a standard component of job interviews at leading software companies in the Wall Street. This phenomenon was influenced but not originated by Microsoft. William Poundstone, a writer based in California, published in 2004 a book titled "How Would You Move Mount Fuji? Microsoft's Cult of the Puzzle, How the World's Smartest Companies Select the Most Creative Thinkers." When he discussed the interviewing process in Microsoft and gave examples of puzzles they offer during their interviews. But the times are changed, so Microsoft is not considered such a hot company any longer. So this year he published a book about Google. Are you smart enough to work at Google? More or less with the same content. The practice of giving puzzles during job interviews remain controversial. Here are arguments against interview puzzles. Solving puzzles is irrelevant to specific skills required for the job in question. Typical interview puzzles are too difficult for the short time allotted to an interview. Puzzles can be vague or based on tricks, with some of them not even having a clear-cut correct answer. There is no convincing documented evidence that persons hired after successful puzzle solving prove to be better employees than candidates turned down after such interviews. And some products of Microsoft definitely support this point. After many interview puzzles and their solutions have been published in books and on the internet, their value has all but disappeared because there is no way to verify whether the interviewee knew the puzzle solution before the interview. Here are arguments for interview puzzles. Interview puzzles seek to identify good general problem solvers rather than specific skills such as coding. Interviewers might not necessarily be interested in a puzzle solution, but rather in the way the applicant has arrived at it. It's the main argument people use. Interviews involving puzzles should be evaluated against traditional interviews, which have been found deficient in several documented studies. And finally, it's possible to alleviate the difficulty caused by the wide availability of a rather limited set of interview puzzles, say by rewording them. Well, one can identify three types of interview puzzles. The first one I call puzzling questions. The second, logic puzzles, and the third are algorithmic puzzles. Here are examples of puzzling questions. How long would it take to move Mount Fuji? Well, similar question. For example, how much would you charge for washing all the windows in Seattle? Or how many piano tuners in New York? Something along those lines. Why are manhole covers round rather than square? In the last example, if you could remove any of the 50 US states, which would it be? I think this is to check a person's politics. Here is an example of a logic puzzle. It's a very old, a well-known puzzle. There are three boxes. One of them has red balls only, one has blue balls only, and the third has a mixture of red and blue balls. The boxes are labeled with labels red, blue, and mixed, but all the labels are wrong. Is it possible to pick one box and pick only one ball from it and then correctly label all these three boxes? And the answer is yes. And here is an example of an algorithmic puzzles. You are at one end of a hallway lined with enclosed lockers. You make n passes along the lockers, returning to the starting point after each pass. On the first pass, you open all the lockers. On the second pass, you close every second locker. In general, on the ice pass, you toggle every ice locker that is open it if it was closed, and close it if it was open. What lockers will be open after the last pass, and how many such lockers will be there. So my personal opinion is that algorithmic puzzles are perfectly all right, quite appropriate for technical interviews. I don't like logic puzzles, and I believe that those puzzling questions are definitely no-no unless you're interviewing for personnel or marketing position. But nobody asked my opinion on this, so let me just advocate for algorithmic puzzles. Unlike the other types of puzzles, nobody can claim that solving such puzzles is unrelated to the job skills needed for success in the software industry. They test the algorithmic problem skills of an applicant in a way divorced from programming skills, which should be tested separately. Unlike logic puzzles, many algorithmic puzzles have reasonable alternative solutions. This allows for evaluation of the interviewee's performance on a more nuanced scale. What's going on in reality? Microsoft seems to be stopped giving puzzles as a matter of policy under the pressure of naysayers. About Google, the story is mixed. Some people say that Google stopped giving puzzles either, and some people say that it's not true, that they continue offering them. But other companies, including the Wall Street, happily continue asking puzzle questions, so you should be aware about their existence. Thank you very much. That's finally the end of the talk.